Okay, let's continue with this. We're talking about the dispatch latency. Okay, dispatch latency. So we want to put all of these things together. We said not only dispatch latency is one part of this one. We told the response interval. So that means starting from the interrupt till finish of the new job. So this is called a response to event. That means for this event, how long it will take from the beginning till the end. So it first have interrupt processing. So you need to interrupt the old job. So here, cannot run that task. We need to run a new one. And then this is for the interrupt related latency. So it's interrupt latency. And after that, you have a dispatch latency. So that means run the new job. This is interrupt the old job. So run the new job, you have two things. So before you start really run that job, you need to have this conflicts phase of dispatch latency. That means you have two phases. The first phase is conflicts. Conflicts means you have some resources contention. So we cannot let the old process or the old task reserve or keep those resources just because the new process or task need them to run. So we have to do two things. First one, maybe it is still using some kernel resources. So for example, we said this is called a preemption of any process running in the kernel mode. So you can stop on the user mode, but you didn't stop on the kernel mode. That's bad because it will still running, but it's useless. So we need to preemption of any process running in the kernel mode. So that means now we need to fully stop running of the old tasks. And the other one is that resource release. Maybe this new task, we need to have some resources occupied by the older task. So we need to have that released by low priority process. Low priority process means this one, because this one interrupt by the high priority tasks. So release by low priority process of resources means release of resources. I think maybe it's better written that release of resources occupied by the low priority processes, which are needed by the high priority processes to be run on the CPU. So after that, it will do the dispatch. We mentioned the dispatch is this one. Okay? Really, we prepare the running. So that means prepare the program counter, load it to the position to run for the new task, and prepare other registers to save temporary variables and so on. So then it's ready to really ready to go to run the instruction. So only after these two types of latencies we are do real calculation, real computing. So this is the time for the process to finish, real-time process execution. So you will add up all of them together to get the response. So response time, just like we mentioned this one when we talk about a process CPU scheduling, what's the criteria? Okay, so this is the idea. Okay, basically we have these two, and then in this one also have two phases. Okay, one is for the stopping CPU, okay, because you are running on the kernel mode but it's still using CPU. So stopping, so it's get the CPU ready to run, and get resources. Resources maybe is file, maybe is memory. Okay, we mentioned in the process synchronization, we have some critical section. So that means for those parts, we access the shared memory. So maybe for this one, we need to release. So like the dining philosopher and the producer consumer, like those things. So they have shared resources. So if they are used, they are needed for the new process. So we must release those resources. Okay, and then prepare for the running start point, running context for the new process. This is really called a context switch. Okay, let's work on some examples. Maybe this is more interesting. So of course, the first one we talk about the priority-based scheduling. So I think priority, of course, you use priority, but what is the priority? For real-time scheduling, of course, we use priority, but how can you decide the priority? Based on what criteria? So later we talk about different priorities. Okay, different priorities. Let's look at the common problem, and then we solve this common problem in different ways based on different criteria to decide the priority. Okay. So for real-time scheduling, scheduler must support primitive priority-based scheduling. The reason is that we cannot keep running a job till to finish, because we have to primitive that job task to run another one to meet some deadlines. Okay, but this one, if like this one, we can only guarantee it's solved real time. Okay, because we only try but don't know whether finally it will meet. So this really depends on how you select priority, but it must be primitive priority based. So that means it can be stopped in the middle, and also we choose jobs based on priority. Okay. So for hard real time, we must also provide the ability to meet deadlines. If we want to perform hard real time, so this one only priority and primitive, and then besides these two, you want to meet if you want to meet hard real time, that means must finish some tasks by the deadline. So you need to add the criteria here. That means not only consider priority, allow primitive way scheduling, but also need to consider the deadlines. Okay. So let's look at the common problems. Okay. So for example, we have some real-time process. So usually we have an important feature for this real-time jobs, real-time processes, tasks. So usually for those things, they happen in a periodic way. So that means they will repeat themselves based on a time range. So that means repeat maybe after 10 minutes or 10 seconds and so on. So this P is just a period. And then it has a processing time. That means how long it will take the CPU to finish its running. That means running time. And also they have a deadline. Deadline, that means when it needs to be finished. So that means, of course, means I can start a little bit late to meet deadline, but you must finish at least by this time. For example, I have 10 seconds for the period, and then 8 seconds for the deadline. And then running time, maybe it's only 6 seconds. Maybe you put 4 seconds, next 4. So that means what is the latest time to start to run this task to meet the deadline? So that one we need to look at this one, right? Because the deadline is 8. That means we must finish by this deadline. So within this period, you will repeat. So even though you have 10 seconds, but you must finish by 8. And then by 8, its running time is 4. So that means latest it will meet the deadline at 8, and then starting to run till the end, no interruption. So the latest scheduling time will be 4, okay? Because 8 minus 4 equal to 4. This is deadline. This is T. This will be the starting time, okay? So T is running time. D is deadline. Deadline, what is the time you must finish? And the T is what is the time needed to finish the job. Then you get the starting time. So that will be the 4. That means latest we can schedule delay starting till time 4, for example millisecond. Okay. So of course we have 0 less or equal to T, less or equal to D, less or equal to P. This is reasonable, okay? Period must be larger or equal to the deadline, and the deadline of course must be larger or equal to the running time. Running time must be positive. Okay. And the rate of periodic task is 1 over P. So rate you can think like frequency, okay? So it's 1 over P. That means maybe later we consider this one as a criteria for the priority, okay? So that's why we calculate the rate here, 1 over P. Okay, so in real-time system we consider these different things. Later when we work on examples for different priority-based scaling algorithms, we'll always look at these 3 numbers. TDP, okay, TDP. Okay, let's look at if we use rate, we just mentioned, okay, use rate. We use rate monotonic scaling. Monotonic means in a increasing or decreasing cut. So that this is just like we based on the rate. So rate as the priority 1 over P, because P is like a period. Period, if it's long, that means you have much more flexibility to finish. For example, I give you 10 weeks to finish the project. Seems you have more flexibility than the one I give you only 1 week to finish. So if 1 over 10 is smaller, okay, that's 0.1, and 1 over 1 week is 1. So smaller one means urgent. You have less flexibility. So smaller means high priority. Okay? For those jobs means you must finish within a short time range. But for long weeks, the P is bigger. So 1 over P is smaller. Smaller value means it has a lower priority. So big value has a higher priority, and small value has lower. So this seems good for us to remember. Okay? So a priority is then based on the inverse of its period, means just rate, okay? That will be the same as rate. Okay. And the shorter periods you have a high priority, because 1 over that shorter period you have a higher rate. Higher rate means higher priority. And the longer periods, 1 over longer periods you have shorter rate. Shorter rate means shorter lower priority, okay, based on the values. Bigger, higher priority, smaller, lower priority. Okay, let's look at an example. For this two process P1, this is P1, okay, want to differentiate. P1, the capital P1, P2 is for process, and the lowercase P1 is for the period, okay. So P1 period is 50, P2 period is 100, and the T1 is 20 running time, T2 running time is 35. Okay, and then based on this P1, P2, 1 over P1, 1 over P2. So you know, so this one is bigger, so higher priority. This one is smaller, lower priority. So P1 has a higher priority. We'll schedule P1 first. Okay. And here, because we only consider the rate as priority, we didn't consider deadlines. but later we'll check whether we meet deadlines. But here we look at the before count. This is only consider priority and primitive, so no guarantee whether we will meet the deadline. So we call it soft real-time. So we can only check later. So because we didn't include the deadline when we do the scheduling, so of course we have no guarantee. Okay? If we add deadlines when we schedule jobs, of course we can meet the deadlines. Okay, because that is the priority. So the not priority is only based on the seems like the frequency, cut frequency. If the frequency is high, since we need to so only consider frequency. So didn't consider its running time. So you can think about what problem it will have. Because if it's a high frequency job, job, if the job is running for long, then the low frequency job, it's running need to wait. They're running need to wait. So they may be missed deadline because they only happened occasionally. But many high frequent jobs, they run in longer time. So longer time occupy the CPU for a long time, and then there's no chance for low priority jobs. So this one is similar like what? Shortest job first, or first come first, maybe shortest job first, like that one. That means only consider FCFS or short jobs for SJF, didn't consider its real priority or didn't fail, is not fail. Okay? Maybe they will be stopped. Okay. Let's look at this example. Okay, P1 is 50, P2 is 100. That's for period. Then you can just write the period first. 50, 100, 150, 200. That will have the P1 period. That means this is the period for P1 period, another second period, third period, fourth period. And then for P2 is 100. That means double the period. So P1 is 50, P2 is 100, and then P2 another 100. Okay, so this is the same idea. So that's why you can find that they have the same, they meet, they intersect here at 100 units of 100. That's because they double this one. And then T1 is running time. Because P1 has a higher priority, we schedule it first whenever it is available. So when we look at the first period, there's two jobs, two processes, P1 and P2. Okay? P1 is also there, P2 is there. But P1 has high priority, so we'll run P1 first till finish. Because here we didn't consider primitive. There's no way to preempt another job because the priority for this one is only always higher than the other one. So we must finish till the end. Keep running till finish. Okay, P1 will run from the 0 till its running time will be 20. Okay, and then after that P2 is still in the queue. So now we are able to schedule P2 because within this period is P2 also there. Okay, so now the CPU is idle, it's free. So it's good to run P2. Okay, from 20 till it's finished, will be, you can find it finished will be till the 55. But 55 is already entering the second period of P1. So at this time we can allow P1 to preempt P2 because now we entering the second period. In the second period for P1, now we have two process waiting, two process available for scheduling. But P1 has high priority, so we can allow P1 to preempt the CPU from P2. So P2 cannot finish till the end. It can only finish the rest time for the first period of P1. So from 20 to 50, only 30 units. And then for the rest, it need to finish after we finish P1 within this period, because within this period P1 is similar repeats the case of the first period of P1 from 0 to 50. That will be the higher priority, higher priority, so can finish from beginning till the end. And then now we can just give the CPU to run the first period period of P2. Okay, the remaining part of the first period of P2. So we run another 5, because T2 is 35. We already run 30. 35 minus 30, we have 5. So from 70 means this is for the 20 for T1. And after that you have the remaining, even though this one have remaining, but there's no other process to run, so it's empty, it's idle. So till 75, we already finish each one at least one time. Finish P1 twice, so it's 40, and the P2 one time. 40 plus 35 is 75. So you can use this one to check its characteristics. So it's 75, you run, because you keep running, there's no spare time for CPU. So till 75, it finish P1 twice, P2 one time. And then till 100, there's no P1 available to run, and also low P2 to run, because the P1 already finished 2 cycles, P2 finished 1 cycle. There's the second cycle for P2 hasn't started, so till here, till 200. And the third cycle for P1 also haven't started. So only after 100 we can schedule another P1 or P2. That means we have a new start. So this new start will just repeat this cycle. You can find it the same, because this one this is independent. This scheduling is independent of this schedule. So that means that you have P1 for 20, and then P2 for 30, and then P1 for 20, P2 for 5 again. So now we check whether they meet deadlines. P1, no problem, always scheduled first for their period. And the P2 also meet the deadline, because this is 100 for the P2, the first period. And this one also meet, of course, repeat. So keeps meeting. So for this one, this case, it meets the deadline, but we don't say it will always meet the deadlines. Okay, let's continue the other case. Maybe it will miss deadline. So miss the deadlines with rate monotonic scheduling. Still the same T1, same P1, but didn't have the same P2. So the P2 period reduced to 80, and the T1 is 25. So different from previous 20, because this is possible. And the T2 is still 37. So these two didn't change, but we changed the P2 and the T1. So this is the same, but this one not the same. Okay, let's look at whether it is still able to meet deadlines. So same, you put P1, P1, P1 here, and then P2, P2 here. But you need to care about the new values. P1 is still the same, so 50, 100, 150. But P2 will be 80, so 80, 160. Okay, and then for here, P1 is still less than P2, so P1 has a higher priority. And then within this period, for the first range, first period of P1, there's only 2 jobs, so P1 is high priority. Always while high priority, you finish it till completion. So we're from 0 to 25. And after that, the CPU is free. We are ready to schedule another ready process. So that means from 25 till 50, still the same as previous. We can only guarantee to allow CPU to run another job which has low priority up till the start of the next period for P1. Because P1 always has high priority with a low primitive. We said it before. For this must allow primitive and priority based. When to primitive? The start point of a new period for higher priority jobs, okay? High priority task. So that means you only can find the switch is at the point for the higher priority task, like this one here. And here no, you can also can think about is change because it's from free to schedule. That means this one will schedule a new one. So same here, right? So at this critical points, you need to be careful to decide which process to schedule. Okay. Same for here, right? Okay, let's look at for P1. Okay, P1. So we run this one till run P1, run P2 till 50. So at 50, we already have another P1 coming again. So that means now it's ready for us to consider preemption. Because P1 is a high priority, so we can preempt the CPU from P2. Okay. So we need to run P1 first, and then for the remaining part we run P2. So P2 for here we run 25 because PT1 is 25. So this is 25, and then for the rest is 25. But the P2 you have 35. 35 minus 25, we still have 10 to finish. And then for this one is also 25, so it means from 50 to 75. This is 75. We are running P1, and then we need to add 10. So till 85, we are running P2. So now we can check whether we meet the deadline for P2 now. So P2 has a period which is 80. So that means within this 80. We have to finish, right? This is a period, and the deadline, we didn't put deadline here, but it already didn't meet this one, right? So deadline is larger than the P, so you can find it larger, right? Because deadline, you finish the deadline, not the real deadline. It's just like you finish time. Yeah, if you think this meet the deadline, then this deadline must be less or equal to the real deadline. This is 85. So 85 less or equal to deadline. So deadline is larger than the P2, small lowercase P2. That's not possible. We mentioned that deadline must be within the period. You must finish within a period. That's the thing we mentioned. P deadline. It must be less than the P. So this means we missed the deadline. Why? Just because this one doesn't hold. This one didn't hold means the deadline is because deadline must be less than P2. So this is 80. But now you finish time is larger than D. So of course we missed deadline. That means within this period, this is the period for P2 from 0 to 80. We finish only at 85. So that's why we said there's no guarantee. We only say this is soft. This is soft. Because we didn't consider all the deadlines. We may meet the deadlines for some, maybe miss the deadlines for others. So this is the case for this algorithm. Seeming like the first come first serve and shortest job first, it may be the not fail for some other jobs. Maybe longest job will wait for there for a long time, staffing, and the first come first served also didn't consider priority and shortest jobs. So that means this seems is only the base case for us to consider, the simple case for us to consider for the real-time scheduling. Okay, let's continue to improve it. So whether you can find a better way to finish this task. Okay. Okay, I think we already used up all of our time. I think we still have several algorithms to two examples to explain. So one is for this one, the other one is for the POSIX example for the real-time scheduling. So we'll keep these slides for the next week's instruction. Okay, that's all for this week, and we'll continue for the memory management after we finish the remaining maybe 5 to 6 slides for this chapter. Okay, see you next week. Thank you. Bye.